So here's a shape I would like to discuss with you a little bit and see if the means of computing the curvature on the surface actually makes any sense for surfaces. So let's have a look at this shape and pick a point, say this one. This is a nice point on the surface. And as we said, there's a unique normal, let's draw it pink like this. It's orthogonal to the surface. And then we can choose a tangent, right? So let's choose a nice tangent, let's say this direction, and see what is happening if we go along this direction on the surface. So the normal and the tangent, they form a plane that looks maybe like this. And if we cut the plane, if we cut the surface along the plane, what we get is a planar curve. So the curve is going to look maybe a little bit like this. And we said that the normal curvature at this point along this tangent is equal to the curvature of this planar curve at this point. And we also said that the curvature is actually the rate of change of the normal, which is bound to the rate of change of the tangent. So let's have a look at what's happening with the normal. So let's say that we went along the curve, maybe down here, and the normal no longer points straight upwards, but now it points in this direction. So if we plot the changed normal back here, we see what's the change of the normal, and it's going to be a vector that looks like this. And that makes some kind of sense because there is a non-zero change, and maybe we can measure the length of this vector and find out that the curvature is maybe proportional to the length of this vector. However, there's a different direction which we could choose, and we'll see that something else is happening there. So imagine that we chose a tangent like this. So what's happening if we cut the surface using a plane like that? What is happening? What kind of curve do we get? And if you choose the right point of view, you will see that the surface is actually completely flat, and we are actually going along a straight line, which I can draw as well. So here, if we go along this direction, we get a straight line, and what we expect is that we are going to get a zero curvature, right? Because a straight line must have a zero curvature. However, if we go along with our computation and compute the rate of change of normal, something strange is going to happen. So imagine that we went over here and the normal now points in this direction. Maybe it's going to be better visible if we go further along, and now obviously the normal is changing quite a lot. And if we then draw the changed normal back here, we will see that it looks something like this, right? So it changes actually, and the change of the normal, let's draw it like this, points in this direction. But we expect a zero, right? We would like to have a zero curvature, and that's the reason why we need to do something else. What we actually need is not the rate of change of the normal, but we need the rate of change of the normal in the direction of the tangent, right? So now the normal is changing, but it's changing in the wrong direction. Here before, in the original case, what we had was a rate of change of normal like this, and it was aligned with the tangent. And if we computed a dot product of the two, then we got a positive number, which is okay because we have a positive curvature. And now you see that the rate of change of the normal, if I draw it here, so this is the rate of change of the normal, and the given tangent, we are going to get orthogonal vectors. and their dot product is of course 0. That's exactly what we wanted, right? So that's the reason for adding something else. We need to compute not only the rate of change of the normal in the given direction, but we have to do the dot product of the rate of change of the normal with the given tangent vector. All we have to take care of now is that we might be moving along the surface at unknown speed depending on the parameterization, but that's better shown using a formula. So let's go back to the slides and discuss this further there.